Thank you, Katerina. It's a great honor to be speaking at this event for the 10 years for the Hausdorff Center for Mathematics. And as Katerina alluded, I'm French speaking, so since you got used to the French accent in the morning, I'll continue using it. Apologies to this morning speakers. So what is discrete optimization? And I should make sure not to fall from the stage. Discrete optimization, well, you got a small taste this morning in Cédric Villani's talk when he was talking about the discrete version of the optimal transport problem. So it's the class of optimization when you want to optimize over a combinatorial or a discrete structure. And our goal will be to derive algorithms to be able to solve such problems. Now, we have to keep in the back of our mind the P versus NP question. And because of this question, typically the problems in combinatorial optimization are of two flavors. The easy ones, like the optimal transport problem, in which you have nice duality, you have convexity, you have efficient algorithms. And then the more difficult one, the intractable ones, the NP-complete ones, in which everything breaks loose. And it's not completely clear where the frontier is between the two. So there is an invisible wall, and from time to time you bump into the wall and you realize, well, you have tried to go a bit too far, and then so it's and so that's going to be the topic of this talk, is to try to illustrate easy and hard problems. So for the easy problems, the optimal transport type problems, I will use the matching to illustrate some of the concepts. And then for the hard problems, I will use the maximum cut problem. And I should say that combinatorial optimization has lots of very interesting and challenging applications. I'm not going to talk about applications of the techniques. And in fact, in Bonn, here, the Institute for Discrete Math has been incredibly successful in solving circuit design problems. So there are a few trends that I'd like to highlight in my talk. I don't want to talk too much about them now. I may not talk as much as I would have liked about probabilistically checkable proofs, but I will definitely talk about lifts of polytopes and hierarchies of convex relaxations. So let's start from a tractable problem. Consider the problem of, given a graph, you'd like to find a maximum number of pairwise non-adjacent edges. And so, for example, here you can get 31 edges, the green edges, and the question is, can you do better? Well, there is a trivial upper bound of half the total number of vertices rounded down, but in this case, that's not tight. So how would you prove that this matching, which may or may not be optimum, is optimum in case it is? So, and that's where duality comes into play, and in this case, duality comes in the following flavor. If I want to delete these 10 red vertices, the graph breaks down in a bunch of components, and if you apply the trivial upper bound to each component, sum them up, and add 10, you get 31. So that shows, this duality shows you that the matching is optimum, and these red vertices is a certificate of optimality. And that was obtained by Tutt and Bunge in the 50s. So the question is, how did I find that matching? How did I find the red vertices that prove the optimality? Well, I'd like to not have to go through all possible matchings and all possible sets of vertices. And so what's important is to design algorithms whose number of steps grows polynomially with the size of the instance. And so in this case, Edmonds 50 years ago derived an algorithm that finds the maximum matching and the red vertices, proving optimality in n cube steps. And so that shows that matching is in P. So let me briefly discuss the P versus NP question. I don't want to get really into it, but P is the class of problems that can be solved efficiently. Matching is one example. The optimal transport, the discrete version of the optimal transport problem of this morning is another one. Primality testing, given a number, given an integer, is it prime? That's also polynomially testable. That was an algorithm of Agarwal, Kayal, and Saxena. And we, in this talk, will be trying to use a lot of convexity. And so we will use the fact that linear programming and also semi-definite programming, and I will discuss what it is a bit later on, are polynomially solvable. So these are also problems in P. I don't want to precisely define NP, but what I'd like to say is that in this class of problems NP, which can be verified efficiently, but I don't want to get into the definition. So in this class, there is a notion of reduction. So a problem is at least as hard as another one. And you can look at the most difficult problems in that class. And these are known as NP complete or NP hard. And for these problems are such that if you solve one of them, let's say the maximum cut problem or the traveling salesman problem, in polynomial time, then you solve all the problems. And P is equal to NP, and you solve the Millennium Prize, one of the Millennium problems. So that's something that we have to keep in mind. And in the last 20 years, there's been a lot of developments on these complexity theory, and especially in the development of probabilistically checkable proofs. And that has a bearing on the optimization problems that I'd like to discuss today, and I will briefly mention. I should say that the common belief is that P is not equal to NP, and so there are no efficient algorithms for these NP complete problems, but there is no such proof. So let me start with an easy problem, and so I already discussed a bit of matching, but let me go over one technique that's often used. So suppose we'd like to optimize over points, a discrete set of points, let's say in S. And so we like when things are convex. So let's convexify. Let's look at the convex solve of this set of points. So we imagine that we have embedded these points in Euclidean space, in Rn, let's say, and we look at the convex hull of them. But we'd like to I mean, it's a bit like this analytic versus synthetic view of it. We'd like to not view these polytope as the Vinci is defining it, but we'd like to represent it as the intersection of a bunch of half spaces. So we'd like to look at the facets of that polytope, look at the linear inequalities that define such a polytope. And if we can do that, then that's great, because then we can use the power of linear programming and the fact that there exist efficient algorithms for linear programming to solve such problems. And there is a caveat, is that when we look at such polytope, they might have many, many facets, exponentially many facets, and in the size of the problem. And these LP algorithms works polynomially only if you have a complete description of the polyhedron. So that's these interior point algorithms. So for these interior point algorithms to be able to use them, we need to have that the number of facets is polynomial. There is another option, is to use the ellipsoid algorithm, which is due to Grötschel, I mean the version, the application to discrete optimization is due to Grötschel, Lovaas, and Scriven, in which what they did was they were looking at showed that if you can separate, if you can, given a point, you can decide if that point is in the polytope, or you can generate a separating hyperplane. If you can do that, then you can optimize over the polytope efficiently. So let's try that for matchings. But before so let me briefly comment on that last line, is that for NP-hard problems, we should not expect to be able to fully characterize the convex cell, but we'll still try to at least partially characterize it. So for matching, such a description of the convex cell was obtained. I don't want to go over the description. What's important is that the number of inequalities is exponential. There is one for every odd set of Vancies. So if you have n Vancies, you have 2 to the n minus 1 inequalities. And so you would not be able to use interior point algorithms, but you could use this version of the ellipsoid. Now, if you're interested in how to use that polytope, for example, or especially similar kinds of approaches for harder problems, like the traveling salesman problem, I put a little information for a beautiful iPhone app that you can download that shows the power of these polyhedral approaches. So the matching problem, the matching polytope that we had exponentially many inequalities. Could we view it in a more compact way? Could you view it in a higher dimensional space and then project it onto a polytope? So for example, if you look at these regular 8-gon in the plane, could I view that as the projection of a higher dimensional polytope that has fewer than 8 facets? And what do you think? Is 8 possible? Can you do better? So I'm not going to, if people volunteer, no? Okay. Well, you can do it with just 6 facets if you go to 3 dimensions. So the first time you see that, that might be a tiny bit surprising, but you know that things in high dimension can, I mean, this is not very high dimension, but still things can go weird when you go to higher dimensions. And so the question, given a polytope in n-dimensional space, could you lift it in a higher dimensional space in which you can represent it by fewer inequalities, fewer facets, and then project it onto P? So I'll define the extension complexity of a polytope, the minimum number of facets that you need in a description of the polytope. So let me give you an example. For example, if you look at the convex cell of all the permutations on 1 to n. So in Rn, that polytope, you can describe it completely. It has roughly 2 to the n facets, 1 for each set of indices, non-trivial set of indices. But it's possible to lift it, and the lifting will have n square facets. And it's simply by looking at permutation matrices. And you know that if you look at permutation matrices and you look at the convex cell of them, well, these form the doubly stochastic matrices by Birkhoff, von Neumann. But you can do better, actually. And this is not completely obvious, is that you can actually go in n log n dimensions and have n log n inequalities, and represent the permutahedron in that space, and that's based on sorting networks based on expanders, construction of Itai, Komlosh, and Zemeredi. And n log n is possible, so you cannot express the permutahedron with fewer facets. So when you look at many easy problems, many of problems in P, and you look at the corresponding polytope, indeed, you can often get a lift with polynomially many facets. So, but can we always do that? And this question was raised about 25 years ago by Yanakakis, and there's been a lot of effort into it. And last year, Thomas Rosvos proved that for the matching polytope, it's a problem that's nicely characterized. We know the inequalities, but you cannot lift it with only polynomially many inequalities. So that's quite surprising. You need 2 to the constant times n inequalities. that was a major result obtained last year. Now, especially when we'll be looking at these NP-complete problems, these hard optimization problems, we won't be able to describe the convex hull completely. So what we may want to do is to look at a relaxation, to look at only some of the inequalities, and that will define a larger polytope. And then we may want to find ways of cutting pieces to get a smaller polytope. And there is a nice way of, there are several nice ways of obtaining this. Let me mention one of them, and that's by a lift and project, which it's called a lift and project. And the way it's done is that you look at polynomials, which are obviously non-negative, on the set K on the polytope you started from, K, and you know that you're interested in the integer point. So I'm assuming that S, your set S, is a subset of 0, 1, of only, it has only 0, 1 coordinates. So for that, you can take it modulo these very simple polynomials, xi squared is equal to xi, because xi is either 0 or 1. And so that reduces this polynomial inequality, reduces to a multilinear polynomial, and you can linearize it. How would you linearize it? You just take any monomial and you replace it. Now, if you want it to be not in too high dimensional space, you'd like not too many monomial. So what you're going to do is you're going to bound the degree of the polynomials you use so that you don't get too many variables. Now, if you do that, you get a polytope in high dimension, which has n to the t plus 1 variables. It seems a lot, but at least if t is 10, let's say, you get a polynomial number of variables. And you can project it onto the singletons and get a tighter relaxation. So for example, from K, you could get K1 and then get K2 and so on by bounding the degree, by using different bounds. And so what one can show is that you get a sequence of refinements, and if you do it n times, so if you take degree n, then you get precisely the convex hull. So this was talking about easy problems in P. Now what I'd like to do for the rest of the talk, do you remember at what time I started? Okay, good, thank you. I'd like to focus on NP-complete problem, and the problem I'm going to choose is the maximum cut problem. It's not a randomly selected problem. In fact, the problem with NP-complete problems is that they are not very stable. They are a small variation completely changes often the complexity and the techniques that one can use to solve them. And I will use this problem because there is a lot of nice mathematics that we can discuss for this. So what is the maximum cut problem? Now, given a graph, like the one on the left, and you might have non-negative weights on the edges, or maybe unit weights. Every edge has a weight of 1, like in this case. And what you'd like to do is you'd like to bicolor the, and maybe I can stay there. You can bicolor the vertices in such a way that the number of edges across the partition is maximized, or the total weight of the edges across the partition is maximized. So for example, in this example, if I do this red-blue becoloring of the vertices, and I look at the edges that have one endpoint blue and one endpoint red, the green edges, I get precisely 15 edges out of 20. So is that optimum? Well, this is an NP-complete problem, so I don't expect to have nice duality like for matching, like for optimal transport and so on. So this might be difficult to show whether 15 is optimum or not. You can go through the 1,000 cuts if you'd like. You can do that very quickly, I presume. And this 15 is not optimum. I could show you a cutoff value 16. And we'll get back to that later on. This is one of the 21 NP-complete problems that were first defined back in 72. And it's still NP-hard if you restrict, for example, to unit weights in graphs in which every vertex is adjacent to only 3 edges. Now, we have to decrease our expectations because we're dealing with an NP-complete problem. So what we'll try to do is we'll try to sandwich the optimum value for a given instance between 2 bounds and that are not far apart. So we'd like to have a bound z and alpha z such that alpha times z such that alpha is as large as possible, and we have a guarantee that the maximum cut value is in that window. So there is one thing we could do which is very simple in this case, is to get a cut which is at least half of the optimum. And why is that? It's because if you take a uniformly random coloring of the vertices, each edge will be cut with probability half. So in expectation, you get at least half of the edges or half of the total weight of the edges. And so you can easily get a cut of value at least that much. And so you have at least half of the total weight. Any cut is at most half the total weight. You get a bound of half. Now, it should be trivial to do better than this. But we should keep in mind that there is this P versus NP question, and we never know exactly where the wall is. We could bump into the wall at any time. And in fact, let me give you just an example of a very surprising NP completeness result, which was obtained from these recent developments on these probabilistically checkable proofs. So suppose I have a system of equations, modulo 2, and each equation has precisely 3 variables. Xi plus xj plus xk is equal to 0, 1. Now, solving it completely, if there is a solution, is easy. We learned that in, I don't know, so if you are from Russia, it's probably in elementary school that you learn how to solve that, or in China too, maybe, but so maybe in high school you learned how to solve a system of equations. I don't quite know. But it's also easy to get a solution that satisfies half of the equations. It's even completely trivial. If you look at the 0 solution, it satisfies all the equations with a 0 in the right-hand side. And a 1 satisfies all the equations with a 1, so you can at least satisfy half of them. We should also be able to do better on this one. But no. So it was shown, Hausdorff showed that if I give you an instance and I tell you it's either 99% solvable or 51% solvable, but I'm not going to tell you which one. And you have to distinguish between the two. I don't even ask you for a solution. Just ask you, tell me, was it 99% or was it 51%? That's NP complete. If you solve that problem, P would be equal to NP, you get $1 million, and you're happy. And everyone is happy, and well, maybe. Life is complicated, so as everyone knows. So getting better than half for max cut might not be as easy as it seems. And one thing that we've seen is that we've seen that maybe we should look at these polytopes. We should use linear programming. So we could look at the cut polytope, which is the convex hull of all the cuts. So for each cut, you look at the characteristic vector. That's in dimension the number of edges. And you take the convex hull of all these all these cuts, and you look at that cut polytope. Now, I said if P is not equal to NP, while there is no polynomial time algorithm for optimizing over the cuts, and so in that case, we do not expect to get a complete description of the polytope. But maybe P is equal to NP, who knows? So, but still, in this sequence of Ronc and in this study of the lifts of polytopes, one of the, so I told you about Hausdorff's result about the matching polytope. Another very significant result in that line of research was the fact that irrespective of whether P is equal to NP, irrespective of that, there is no lift of the cut polytope that has fewer than exponentially many facets. So it's not that we can expect to write a polynomial size linear program and optimize over it. That's out of the question. Now, but what we could do is we could try to look at some of the inequalities, some of the facets of the cut polytope, and look at that relaxation. And then possibly use this lifting procedure I showed you to get better relaxations. So there is an easy one to describe, and which is called a semimetric polytope, and it's motivated by the fact that if you look at a cut with, and you say that for two vertices across the cut, let's say the distance is 1, and for two vertices on the same side of the cut, the distance is 0, that's a semimetric. And so you could try to get inequalities defining semimetrics, and when you do so, these inequalities, but you shouldn't look at them. So some inequalities come up. Again, we have exponentially many inequalities, and so even for that relaxation, it's not completely clear how you optimize efficiently over it. But still, we can do it. In fact, there is a lift of that polytope in n square dimensions that has only n cube inequalities. So if I write that lift, and again, don't look at it too closely, the message is that I can optimize over this in polynomial time by just looking at this polytope. So you can look at that polytope, and we can optimize over it, and we get a bound. So this is the maximum cut value. We have cuts of some value. That's the maximum cut. And then we're optimizing over a larger polytope, so we get an upper bound. And we could ask, well, what's the ratio between these two? Because if the ratio is good, I might be able to get a good approximation for the problem. Unfortunately, it's half. So it's no better than the bound of half we got. And the examples are quite simple. For example, you could take a random D regular graph. That will, and D, if you take a random D regular graph and D is large, that will give you an example. If you want a deterministic construction, it's a bit harder. But if you look at the Ramanujan expander of Lubotsky, Phillips, and Sarnak, they have the property that the maximum cut is about half of the number of edges, but there exists a value to the linear program that gives almost 1 to every edge. So it looks like all the edges are fractionally in the optimum cut, but the optimum cut is only half of that. Now, this is annoying, so we might try to lift the polytope and go to a higher dimension by using this Shirali-Adams hierarchy. Unfortunately, if you do that, even if you do 10 levels, if you multiply by these non-negative polynomials of degree 10, let's say, and you put all these inequalities, these Ramanujan expanders will still be bad instances. So that's bad. So you might say, okay, forget about these Shirali-Adams, these constructions. we might look at other sets of inequalities that we can write. I'm sure that we can think about inequalities that all the cuts have to satisfy and try to write them. But if we want to use linear programming, most likely we would just write a polynomial number of them. And in a fairly surprising, in a very nice work, it was shown that if you write n to the 10 inequalities, that's not going to be better than doing 2t rounds of Girali-Adams in the worst case. And so linear programming will not be able to, most likely will not be able to give you a better than half approximation algorithm for max cut. So we have to think about other ways of approximating cuts. And so about 20 years ago with David Williamson, we suggested using semi-definite programming. And let me tell you what it is. So let me first derive you the semi-definite program that we use for cuts. So you can look at the problem of max cut as a, maybe I should go on the table, but that's probably not advisable. If you can write it as a quadratic form in which you optimize over all minus one vectors, this quadratic form. Now, it's 2 square, it's 4 if an edge is minus 1, 1, and it's 0 if an edge is minus 1, or 1, 1. You can also conveniently write this as the Laplacian times this rank 1 matrix, XX transpose, where this inner product is inner product over symmetric matrices, the Frobenius inner product. And so you could, when you look at this formula, so the Laplacian is just, you just take the, it's the discrete Laplacian. It's just the summation, a weighted summation of these matrices that have just a 1, 1 and a minus 1 for the endpoints of your edge. And so when you look at this form, suppose that I replace XX transpose by Y, while clearly Y is positive semi-definite. The rank is 1, obviously. The diagonal elements are all 1. And the weight is a linear functional of that Y. So good, linear is good. This is good too, because that's convex. The cone of positive semi-definite matrices is convex too, so that's good. So the only thing that's bad is about this one, the rank being 1. That's a non-convex constraint. And so just forget about it. So we're optimizing over all matrices that are positive semi-definite, that have diagonal equal to 1, and we're optimizing this linear functional. So that's essentially the class of semi-definite programs. So that gives you an upper bound. And the nice thing is that you're in the world of nice convexity, duality, and so on. And so you can compute. This seems to some extent harder, but it's much easier than computing the maximum cut. So you can compute this up to epsilon in polynomial time. So even for a graph with 1,000, 10,000, whatever, you can compute this value at least approximately in polynomial time. And so you get this semi-definite matrix. Why? That's not the problem I wanted to solve. I wanted to find a cut. So now I'd like to be able to recover a good cut. And I'd like to know if this bound is better than half. This upper bound, is it within a factor of half of the optimum cut? So here is one idea: is you take this semi-definite program, you view it as a gram matrix. So you view Yij as the inner product of Vi and Vj, in which Vi and Vj are unit vectors. And So for example, if I take the original graph and you solve the SDP and you look at these vectors nicely will lie not in 11-dimensional space, but in 3-dimensional space. I mean, that's why I use that example, because I could plot it on the screen. And so you should look at, there is a unit, there is the sphere that I did not draw. But now I'd like to recover a cut. And the intuition behind this embedding is that if I have two vertices that are far apart, I'd like to put them, to separate them by the cut. And if they are close together, I'm fine with leaving them on the same side because they don't contribute much to my objective, my linear functional. So I'll take a cut, just a hyperplane cut. So I'll use the geometry in this case. And I use a hyperplane cut, and I'll just look at the vertices on one side of my hyperplane to be on one side of the cut, and the vertices on the other side to be on the other side of the cut. So in this case, it gives me a cut of value 16. So that 15 was not tight. And the upper bound that we get from this semi-definite program is 17.18, so there is still a little bit of room, but cut is 16 is optimum. I could prove it to you, but I'm not going to. And now which hyperplane do you use? Well, it's not clear. So let's do it randomly. Let's take a Gaussian and R, and then let's just look at the vertices I, which have a non-negative inner product with that Gaussian vector. And in this case, if we compute the expectation of the cut, of the weight of the cut that you get 15.11. So this is, I mean, so you have an upper bound, but you have also a lower bound. And the cut that you will generate will be in between. Now, the algorithm is very simple, and the analysis is even simpler. It's actually, it's embarrassingly simple. So, but first, let me give you what the performance guarantee is. So if you do that, the claim is that the expected weight of the cut you get will be at least alpha times the maximum cut. In fact, it will be at least alpha times this upper bound that you generate. And that alpha is given by the worst case ratio between these two functions. R cosine of rho divided by pi and 1 minus rho divided by 2. And these two functions will appear very often in the next 10 minutes or so, right? So let me write them down. So it's R cosine of rho divided by pi divided by 1 minus rho divided by 2, and you take the minimum over all rows. You could either 0 or 1, it doesn't. I mean, the minimum is attained at something like minus 0.8 also. In fact, I think I have a picture, probably. Yes. So this is the linear function 1 minus x over 2. That's the R cosine. The minimum between the two is given roughly here. And that gives you that, when you compute that minimum, you get 87856, roughly. Okay? So, and let me show you the analysis. The analysis is trivial. It's simply that, what's the probability that an edge is part of my random cut? It's simply, you take the corresponding two vectors, Vi and Vj, you're in n dimensions, you generate a Gaussian, and the question is, what's the probability that these vectors, the hyperplane normal to it, will separate Vi and Vj. It's easy to see it's a two-line argument or one-line argument that it's equal to the angle divided by pi. And so you get a closed form formula for the expectation, and you can compare that to the SDP value, and you get the bound. So it's embarrassingly simple, and it gives you a bound of 87856. Now, so semi-definite programming has been used extensively, and the reason is that it's convexity again. Convexity, convexity, convexity. So, and it has nice duality as well. And for max cut, if you write, so the way I wrote the semi-definite program, it's a maximization problem, but you can also view it as a minimization problem, and there is no duality gap. And when you interpret the dual, it's simply the largest eigenvalue of the Laplacian, in which you can improve it by modifying the diagonal entries in a certain way. So, and that was shown first by Delorme and Polyak, and unfortunately, with that dual version, you don't see how to get a cut. So from this eigenvalue bound, so it's not clear what, how to get a cut. So that does not allow this nice analysis. Now, by the way, for my Ramanujan expandon graphs, we know the spectrum. We know that the eigenvalues of the Laplacian will either be 0 or between d minus 2 square root of d minus 1 and d plus 2 square root of, highly concentrated around d. And so you can show that indeed Ramanujan expandon graphs have the max cut at most roughly half the number of edges. So let me just say that semi-definite programming has had lots of applications, but I don't want to get into that. Let me discuss now whether the analysis can be improved. So, so I showed that if you look at the SDP value divided by the expected value of the cut, that this ratio is always at least this 0.878. But in fact, you could break this ratio into two. You could view it as the SDP divided by the max cut, and the max cut divided by the expectation. And so the first thing I'd like to show is that, in fact, oops, wrong way. So it should be, so max cut is smaller than SDP, so let me put max cut divided by SDP, and both of these are less or equal to 1. And the product is at least 0.878. But let me first show that max cut divided by SDP can be as arbitrarily close to this 87856, and it's a nice geometric construction. So, so that was done by Feiger and Skekman. So what you do is you take a d-dimensional sphere, you put a very dense collection of points on it, and you put an edge only if they give you an angle that's the worst case rho. Then. And so if you do so, you can show that, first of all, the embedding, the obvious embedding, I mean, I constructed it on the sphere, so that's an embedding. So that embedding will be an optimum solution to the SDP, or at least it will be. I don't even need that. I need only that it's a feasible solution. So that will give me that SDP is at least that, and then I will need to show that the maximum cuts are given by hyperplane cuts, and this can be done by concentration of measure and also an isoperimetric inequality on a continuous analog. So this discrete setting is difficult to analyze, but when you look to when you go to the continuous analog, you can get such an isoperimetric inequality. But it can also be, so this could be 0.878, but this could also be 0.878. So there are some different classes of instances, and this one is even more interesting, and I'll tell you why in a second. So we could have the case that this one is 1, so the SDP is essentially optimum, but the gap here is 87856. And the construction is the following. What you do is, it's a random construction. We could give a deterministic construction, but let's say this is better for the analysis. So your vertex set is minus 1, 1 to the m, so the m-dimensional cube, and you put all the edges, so it's a complete graph, and the weight of an edge is essentially a Bernoulli random variable. So what you do is you take between x and y, you start from x and you flip the coordinates of x with probability 1 minus rho over 2. And you put as weight of that edge the probability that you get y. Now, I'm not going to go over this, especially since I'm a bit short of time, but one can show that you get that by looking at the eigenvalues of this construction, you can see that the SDP is the denominator term, and so is the maximum cut. But the optimum cuts in this case, so remember it's a cube, the optimum cuts will be coordinate cuts. While the hyperplanes, the random hyperplanes, will be far from coordinate cuts. We're in high dimension again. And so the hyperplane cuts will be roughly r cosine of rho over pi. So will be in the setting in which the hyperplane cuts will be the numerator, but there will be much better cuts, which are these coordinate cuts. But one result that's key for the next slide is actually a result of Mosul, O'Donnell, and Olesinski, which apologies. I should have done. I should have put MOO like in Cedric Villani's presentation. That would have been much better. But what appears by Fourier analysis, what you can show is that if you have a cut that differs from a coordinate cut in a significant way, it will actually be like a hyperplane cut, and not like a good cut, not one like a max cut. And so that's going to be crucial to actually for some recent result, which is which I've denoted at the bottom, which actually shows that this 87856 would be the best you could do unless p is equal to np, but also, unfortunately, you need another assumption as well. An assumption that comes, a conjecture that comes from these probabilistically checkable proofs, which is known as the unique games conjecture. I don't want to define that conjecture. In fact, there is not a consensus on whether that conjecture is true or not, but let me explain it in a different way. So let me explain it in the following way. Suppose that you had a system of equations modulo m, and very simple equations. Xi minus xj is aij. Now, clearly, again, solving all of them is easy. Getting a solution that satisfies 1 over m of them is easy also by a simple random choice. But the question is the following. Is it true that for that there exists a delta and an epsilon, let's say 99% and 1%, so that you can distinguish between instances in which you have at least 99% or at most 1%. But I'd like that 99% and 1% not to depend on m. So the 1 over m bound is too weak. And so what this analysis of the cube that I gave on the previous slide and these probabilistically checkable proof constructions show is that this 87856 algorithm that I showed you has no consequence on this. However, if you can improve it by epsilon, then you could answer this question. And this question people have looked at from different standpoints. There is no 87856 that appears on that. I mean, it's just seems, so from this it seems that 87856 might be where the wall is for the maximum cut problem, although maybe we can do better and be able also to solve that problem. Now, let me finish by saying that semi-definite programming has been used in many other contexts, and one way that has been very nice is to, instead of in the Shirali-Adams construction, we were looking at polytopes and then getting strengthening of them. We could actually do the same thing with semi-definite programming, and one nice way to do it is through real algebraic geometry and try to express, so view a problem as a polynomial optimization problem in which we'd like to, let's say, maximize a polynomial subject to polynomial inequalities. And then what we'd like to do is we'd like to try to prove that given a certain value lambda, we'd like to prove that lambda minus one polynomial is non-negative over all 0-1 solutions. So, or over some ideal. And so what we'd like is we'd like to construct a proof in which we have a sum of square certificate that indeed lambda minus f is non-negative. And so by bounding the degree, if we bound the degree, then this can be done in polynomial time. Finding a sum of square proof is equivalent to semi-definite programming. This can be solved by, it's not equivalent, but it can be solved by semi-definite programming. And so we can get a sequence of bounds for any t that gives us a hierarchy of bounds on an NP-complete problem like the maximum cut problem. And one question is, if you use these hierarchies, if you use these stronger bounds, could we get better approximation for max cut or other NP-complete problem? And not much is known. It's known, for example, if you do one level. So if you do, I forget always if you have to take, so that's, if you do t is equal to 2, it's known that that's not true, that you don't improve, but maybe you could go to a higher level and improve. And so there was P versus NP was the beauty and the beast, and to some extent I hope I convinced you that there is some beauty in the beast. So, thank you.
So, thanks very much. Are there questions? Comments? Yeah?
Yeah, I was expecting one.
So it's very simple question. I did not get when you explained about the Birkhoff theorem, how you use it to get this with n square faces in a high dimension, giving your original polytope as projection. How do you, is it simple?
Yeah, it's very simple. So if you look at n by n matrices, just permutation matrices, and if you look at the convexal, do you agree that that's the doubly stochastic matrices, so the non-negative matrices which sum to 1 in both rows and columns? Now, you take that space and you just project it by multiplying by your vector of 1 up to n. And the corresponding vector will be a vector in your permutahedron. And as you go over all permutation matrices, or all the convexal of permutation matrices, you go over all permutations on all the entire permutahedron.
Okay. And you said, but you can do much better with n log n, but then it's much more complicated, is right?
Yeah, so essentially, so if you look at the procedure of sorting n numbers in a myopic way. So suppose I put n numbers, and the only thing I'm allowed to do is I can take two numbers, compare them, and I can switch them if depending on which one is bigger. So if I'm allowed to do that, if that's my model of computation, one can show that you can do it in n log n steps in a way that's based on expanders. So it's easy to do it in n log square n, but it's not so easy to do it in n log n. You need the machinery of expander graphs. So to get explicit construction of these sorting networks with n log n is actually not that easy. But then once you have such a sorting network, getting a lift for the permutahedron is kind of easy, because what I could do is I could say, well, if you give me numbers and you sort them, you should get 1 up to n, if this is a permutation of 1 up to n. And so I'm just going to impose that you get 1 up to n, and I'm going to look at what you fed into the network, and that's going to be my permutahedron. And looking at all the values will be my lift of my permutahedron.
Any more questions? Yeah.
So in the work of Mossel, he uses Gaussian noise stability to apply it to max-cut problems. Is there also a kind of continuous version behind these problems which you presented? Is there
so this is precisely, so I didn't say anything about how this last statement is proved, but indeed it. So this is a result about the Boolean cube and -1 random variables, but you have to show, to prove this, you have to show that there is some kind of universality principle, and that's when that they get it from these Gaussian.
Okay.
So, I mean, the way I stated the statement is very informal. So you need to look at the Fourier coefficients and look at the one that have small support and blah blah blah.
Okay.
So, but I don't want to discuss that.